Okay, let's try it out. We've got our increasing, decreasing test. This is how we can identify where a function is increasing and decreasing without even seeing the graph. And we've got our example here, the first one. Determine the intervals of increasing and decreasing for part A. F of x equals negative x to the third plus 3x plus 5. Okay. First thing we need to do, step 1 of our test, is to identify the critical numbers. So we need the derivative. There's our derivative right there. F of x was negative x to the third plus 3x plus 5. So our derivative, well, we just got our power rule right. The polynomial f prime of x equals negative 3x squared plus 3. Okay, no big deal there. Now, we need to do two things. We need to set the derivative equal to 0, and we need to figure out, are there any x values where that derivative will not exist? So let's look at setting it equal to 0 first. I'm covering up the other side, so we're going to just say, hey, equals 0. And we'll go ahead and solve. And this one isn't giving us too much of a challenge. That's nice. We subtract 3, divide by the negative 3, take a square root. Square root of 1 is 1, of course. So we end up with two critical numbers by setting it equal to 0, positive and negative 1. Okay, so we'll keep those in mind. We also need to think about, hey, are there any x values where a derivative does not exist? Think, okay, well, for this function here, no, every x value is going to be okay. There's no x value that causes any problems there. We will see functions later where this will have an answer. But for now, negative 3x squared plus 3, no value that you plug in is going to give any problems. There are not any x values where the derivative does not exist. Okay, so we wound up with just these two criticals. The next step was it said to mark these on a domain line. So we want to note the domain of our function. Our original function was f of x equals negative x to the third plus 3x plus 5. And we can realize the domain of that is everything, right? There's no values of x that give us any problems there. Really, you're thinking about like vertical asymptotes, maybe holes, or maybe just certain values of x that would cause you to take a square root of a negative. We don't deal with any imaginaries here. Things like that. It's not unusual for the domain to be the entire number line, but occasionally you got some values you have to skip over, that sort of thing. Okay, so here the domain's everything, so I'm going to draw a number line that matches that domain from negative infinity to infinity, and I'm going to mark those two critical values at negative 1 and positive 1. Okay. So that was like the beginning of step 2. On a domain line, mark the critical numbers. All right. Then it said to test each interval in f prime of x. Now what does that mean? When I mark my domain line, I've created 3 intervals. This one here in the middle, and this one. So I'm going to take a number, any number, from each of the 3 intervals, and I'm going to plug those one at a time into f prime of x. And that's going to tell me which of these intervals are increasing and which are decreasing. So how's that going to work? Okay, well, let's try it out. What is a good value to pick that would, from this first interval? It's kind of like be that the representative from this first interval. I think, well, if that's -1, let's pick -2. Okay, let's pick -2. Oh, and I've got some more instructions there. Kind of what I said verbally. Plug one value from each interval into the derivative. Okay, so for this first interval, I'm going to say, well, it's got to be something less than -1. Let's make it easy on ourselves and pick -2. So I'm going to plug -2 into f prime of x. F prime -2. So here it is. -3 times -2 squared plus 3. Remember the derivative. It's off the screen now, but it was this. Right? So if I plug -2 in, I'll let you guys confirm that that gives -9. Okay. Here's the thing. It's not important what the number is. It's only important if it's positive or negative. We got a negative answer, so you see I put a negative sign there, and I'm actually going to go back up here and put a negative sign. And I like to throw a circle on it, just so it's really clear to me on the page. This interval has a negative derivative. Hey, if this interval has a negative derivative, then that means the function is decreasing right here. From -infinity to -1, the function is dropping. Negative derivative. Okay. Well, let's go on to the second interval in the middle. What's a good value of x to pick to represent this interval? Say, well, -1 and +1. Let's pick 0. I think that's a good choice. That doesn't matter what number you pick. But if you have a chance to pick 0, I say go for it. So I'll pick 0 for that middle interval. We're plugging that into the derivative, and we're just concerned with, do we get a positive result or a negative result? Well, plugging in 0, we get +3. That's a positive, so we know that every value in there is going to have a positive derivative. So the function is increasing between -1 and +1. Okay, we got one more to try out here. Well, what's a good representative for the interval above 1? Well, let's just keep it as simple as we can. Let's pick +2. You could pick 10 or 20 or pi, anything like that. But keep it simple is what I recommend. Okay, so if we plug 2 into the derivative, well, we happen to get -9 again. I mean, we've got this symmetry kind of happening. Not important that it's -9. It's a negative, so I'm going to put a negative right here. And that tells me I'm decreasing again, so this function goes down, and then it goes back up, and then it hits +1, and it goes back down again. And with that, we're able to answer the question. F of x is increasing between -1 and +1. F of x is decreasing from -infinity to -1, and then again from 1 to infinity. We've got our answer. There it is. Okay, very nice. Let's try a harder one. So I have to grab some papers from right over here. Here we go. Part B. Now this one is not the simplest version. It's not just a polynomial, although hopefully we're all pretty comfortable with taking that derivative. There's more to it than that, right? Okay, f of x equals the quantity x squared minus 4 raised to the 1/3. So if we're going to see where this function is increasing and decreasing, right, first thing we need to know are the critical numbers. And in order to get the critical numbers, we need the derivative. So let's go for it. Now, if we were in class, we'd probably talk through how to perform that derivative. But I'm hoping something like this, by now you're pretty comfortable. Right, we've got a chain rule. So the 1/3 comes down, drops to a negative 2/3 when you subtract 1. Copy this part, then multiply by the derivative of x squared minus 4, gives you 2x. Now, because we're going to do more than just take a derivative, I'm going to rewrite this in a style that's a lot more conducive to setting equal to 0 and solving. And I recommend you do the same. I'm going to rewrite it this way. That 1/3, that 3 is going to go down there. The negative exponent is going to put this whole thing in the bottom, and that 2x is going to multiply up to the numerator like so. 2x over 3 times the quantity x squared minus 4 raised to the 2/3. And this will be a lot easier when it comes to our next step in finding the criticals, right? Cover up what I've got over on this side. We need to set that thing equal to 0. And solve for x. Okay. Well, let's see. This can be a bit intimidating. That's quite a fraction there on the left, but it turns out in one easy step, this will get a lot simpler. Here's my advice. We're going to multiply both sides by this denominator. That whole thing, just multiply both sides by that. Well, if this multiplies over, hey, guess what? It just multiplied by 0. And we're left with 2x equals 0. Another way to think of it, some people prefer this. Instead of multiplying both sides by the denominator, they think, hey, if a fraction equals 0, doesn't that mean the numerator would have to equal 0? And that's another way you could come to this conclusion. Whatever the case, when we solve that, we got our first critical number, x equals 0. Okay, that's one. Turns out there are more critical numbers. So over here, we also need to consider when our derivative does not exist. So, okay, now we will have some answers. Is there any time when this expression here, when that function will not exist? Well, now I see x appears in the denominator. So sure, if my denominator ever equals 0, then the derivative will not exist, right? It will be undefined. So I'm just going to take my denominator only and set it equal to 0. Then I can divide by 3. I can do whatever I need to do to get rid of that power. Raise it to the 3/2 would cancel that. In the end, really, it just boils down to what's inside there equaling 0. And then that gets solved pretty quickly. X squared equals 4. So x equals positive or negative 2. So now I've got 3 critical numbers. And I'm going to go, okay, what's my next step? After I have all my critical numbers, I take note of the domain. Here again, the domain of my original function is everything. Negative infinity to infinity. So if I draw that domain line and I mark my 3 critical numbers. Now, it doesn't matter how you scale it. What matters when marking your critical numbers is that you do them in order. So -2, 0, +2, you know, this is a number line, right? Okay. Now I ran out of room on this page, so I'm going to go ahead and continue it up here, but I'm going to draw, I've drawn that number line again. So that'll be, we need to have that to reference. Okay. And same procedure as before. This time though, we have 4 intervals to test. So we need to pick a value from each one, and we're going to plug it into our derivative. If you remember, our derivative was this. Much easier to plug it into this simplified form as the fraction. Much easier to plug numbers in. I'm going to say, okay, what would be a good choice for that first interval? Well, anything less than -2 would work. I'm going to recommend -3. And I'll just show you all of my computing there. Plugging -3 into our derivative. In the end, it will get you -2. I recommend, you know, go ahead and compute that as you're watching this. Maybe pause the video and do that computation. You're probably pausing already just to copy everything that I've got written here. Okay, in the end, the point is when I plug in -3, it comes out to -2, but I don't even care that it's -2, it's a negative answer. So I like to go back and put a big negative sign there and circle it. And okay, I think we get the idea. It's a lot, I don't know if I'd say a lot, but there's definitely some number crunching, some tedious work here. Moving on to the next interval, how about we pick -1? And you may be surprised that this comes out to a negative as well. It's not guaranteed to alternate positive, negative. Sometimes you do get the same sign back to back. Okay, if we go to the next one, maybe we pick +1. Again, there's a decimal here. If you don't get a pretty answer, you know, by plugging in -1 or +1, I rounded it just to give myself an idea. But of course, again, it's not even the number that matters. It's just the fact that that's negative. +1 gives you the same result except the positive version. So I don't care what number it is. These are rounded decimals. It's just the fact that it's positive. And then finally, something bigger than 2 for that last interval. I picked +3. And what do you know? There's some symmetry here. It's not uncommon, not always, but not uncommon that I got, you know, -2, +2, negative, this decimal, positive, the same thing. And we got another positive there. Okay, so I can tell I'm ready to answer the question. My function is decreasing here, it's decreasing here, increasing. One thing people will ask is, what about like -2 itself or +2? Can I just say it's decreasing from -infinity all the way to 0? And can I just say it's increasing from 0 all the way to +infinity? No, because at -2 and at +2, it's a critical number, and it's not increasing at either of those. In fact, it does not exist, right? The derivative did not exist there. Turns out there's a cusp here, and there's a cusp here. So even though this is true, at that point itself, we have to skip. So here's what we'll say. It's increasing from 0 to 2, and then from 2 to infinity. We skip over 2 itself. And our function is decreasing from -infinity to -2, union -2 to infinity. We have to skip the -2. So in the end, we've got 4 intervals, just like our number line had 4 intervals. And there you are. I think this is a good place to stop. We will talk about local maxes and mins next.